Hello everyone, welcome to Wolfram U's webinar series Learning about LLMs. My name is Abrita Chakravarti. I'm with the Wolfram U team. It is my pleasure to welcome you all, and we hope you are going to enjoy this session, learn about neural networks, learn about LLMs. Our speaker today is Giulio Alessandrini, lead developer for machine learning at Wolfram. He will talk to us about going from neural networks, which we introduced in our last session, going from neural networks to large language models. Without further delay, I would like to hand over to Giulio for his presentation today.
Hi, Abrita. And hi, everyone. So I'm Giulio Alessandrini. As Abrita said, I'm a lead developer of the machine learning team here at Wolfram. Just wanted to introduce myself in person, but I guess without further ado, let me start the sharing so we can start looking at some content now. I'm gonna start this by doing a quick review of what entails to train a neural network. Gonna take it slow, like hopefully connecting well with what Abrita explained last time. And then I want to remind you that after my talk, it's a bit more technical. There's another much more fun session with my colleague Joffre that is going to go through like kind of what's cooking about like new exciting tools built around language models. So I hope that my talk will give you kind of some more like understanding and explain how to play with this model a bit at a more like technical and then a close to metal way in the Wolfram language. Okay, let's begin. So in this session, we are gonna, as I said, quickly review what it means to train a neural network. Given that this network training basically is a very numerical thing, I'm gonna briefly touch on how do we represent complex objects like images or text in the case of language models with neural networks, and then we're gonna go through the gory details of how you train a transformer model, which will allow me to kind of demystify a bit and show a bit like how these work internally. It's not like, I promise, not too complicated. Okay, so let's start. What happens during training? So you have seen commands like net train in the previous session, like that fires up an optimizer. There's a lot of complicated machinery going on under the hood, but generally speaking, what happens is that when you define a network like this, like I'm using like this simple syntax to define a network that takes like a 3 linear operation, like this linear layer. One outputs a vector of size 4, one outputs a vector of height 3, and one, like I'm using this empty list to say that is a scalar, and there's like 2 non-linear operation in the middle, which is a ramp function. So like this is my, like it's very quick to define it this way, and I say this should take a real number as input. So like this is my network, and so I wrote this function. This is not a language function, so I deployed this in the cloud. So if you have this notebook, you can like easily use it, which is taking one of these networks and basically coloring all the connections. And you can see very easily that if you have like this is a real number that comes in input, and you have like 4 real numbers here as the first output, and 3 is the second output, and this is the final scalar. And then you see some colored arrows. So what are these colored arrows? These are the parameters value of the model. This is the stuff that actually computes and that we are gonna tune during the training. So the colors here, they indicate the value. I believe that like redder is the more positive, the bluer is the more negative, and then we go to yellow gray in the center. So we can put one value in input here, and then you see, for example, if I put 1, this takes this neuron, so-called, takes a value, and so this comes from when these were like inspired by biological networks. This takes a value, and basically these multiply this value by these weights, so I get new values, and then again I get new values at the second level, and then I get new values at the third level. So of course, if I change the input value here, like this now it becomes blue. I get like all different things here. So yeah, basically this is a very small network, but a big network is very similar to this. Is just having many more of these, like has like billions of these units. So I'm not gonna plot anything like that here. It's completely incomprehensible. But yeah, the idea is that during the training, what do? You monitor what is the final value here. You measure some error against what your desired output is, and then you try to fix these parameters. So at the beginning, these parameters are random. So here, for example, I initialize this network 4 times, and you see that this takes a real and outputs a real, so I can easily plot the result of this network. This you can see this as a random function, and so you see now, for example, this connection multiplies by a big negative value here, by a positive value here, and the result is that these are basically different initial values for my function. Then once I set a task, for example, I set this task, like learning a parabola, then I can start like evaluate this, right? So I can start like trying to minimizing the difference between like one of these and this one, and basically the core of the loop is that I take a derivative, if you are familiar with calculus, of this error, and I just see how I can like fine tune little by little each one of these arrows to make it like better follow the desired output. So let's see something more in detail. So like you've already seen, if you put things in a net train function, you get a panel like this that tells you like a bunch of things that are happening and tells you what the error is. Hopefully it's going down if you're doing stuff well. And then a bunch of other stuff like how much time has passed, how many examples the function has seen. But these are we don't need to go into those kind of details. There are things that you can customize this. So this is a bit more difficult to do. So I put some code to kind of show what can be done. So here I'm using the same plotting function as before, and I can evaluate this now. Actually, this is an image. Okay, this is an image that I put here. But you see, like these numbers, they are changing live because I'm training the function. Yeah. So this is the number of example groups that I'm showing, and the more I show, the more it adapts and then slows down. And now this result here doesn't move much. So this is what is changing internally, and this is happening, of course, for like stuff like language models at a much higher scale. But the core concept is this: you send an input in, you propagate it, you look at the end, you check for the error, and then you propagate back, and you fix basically the error value. So what is in the forward pass, what is called when you put the input in, these values of the errors are fixed, and then you compute what happens. And in the backward pass, you tweak each one of these arrows to minimize this error. So okay, we can stop this now, and you can stop these optimizer at any time and get out a partially trained thingy. So another thing that you can do, for example, here I define a function that takes what is the batch. The batch is just the group of examples, because these models are not trained on one example at a time, one point at a time. They're trained on a group. So in this case, group of size 50, and then it's plotting it together with so it's a series plot with the original data, the data you use for training, and a plot of the function that has been learned. So if I evaluate this, then you see, now this is actually how the result is changing live during the training. Yeah, it's selecting a bunch of these, and I'm updating a new frame every 20 batches of examples, and then like slowly but steadily is trying to converge. So you can see like in this case, I'm influenced by the structure of the network. You see a lot of like this kind of piecewise function here. Why? Is because I'm using ramp nonlinearity. So if you're not familiar with ramp, I can show you plot ramp of x. X goes between like -2 and 2. This is ramp, yeah. So it's like identity here and 0 here. So this creates this kind of piecewise structure. We're going to see like different ways you can put this stuff together. But yeah, just for the time being, and this is a very, very, very quick refresh of simple neural networks and what happens when you train them. Okay, so an example like this, it's quite easy to visualize. Is a function from real numbers to real numbers, but what happens when we want to deal with more complicated things, like images or text is what we care about here. So let's start with images because it's a little easier. So the idea here is like starting from the assumption that neural networks only works with numbers, with matrices or tensors of numbers. We need the proper numeric representation for everything we want to train on. Let's say this is a very famous network. It's called LeNet, and this is trained to is a basic classifier. It takes an image in and gives you an integer digit out. So in this case, the images are probably you've seen this. It's a very, very popular one. The images are grayscale, so it's like only one color channel. They are all fixed 28 by 28 pixels, and the output is like they go from 0 to 9, so the output is a number from 0 to 9. And you see this is a slightly different structure, it's a little bigger network, but the core here is that at the beginning I need to do something like this. Yeah, I take my image and I represent it as an array. In this case, a matrix of numbers. There's an extra list here. It is more, but you can notice this is because this is a one-channel image, but this can also work with colored image, which will have like 3 matrices like R, G, and D, red, green, and blue. It's like a generic structure for like any number of channels. So you take this, and then the bulk of a network, like everything you have here, this filtering operation, you see there's a ramp again. I'm not going too much into details here because we don't want to analyze too much images network, but all of this is done to process these metrics and transforming it into a vector. Because if we can encode in few numbers what is the content of this image, then we can use these numbers to do interesting computation. So in our case, interesting computation is try to find out what is the economical content, like what is the class of this image. I want to find one between 0 and 9, I have 10 classes. And I want to use this feature representation, which is also called embedding, because I take an object like an image and I put it inside a vector space. I want to take it and use to do things. So I have this, and then if you look at what this network is doing, except for the final part, I'm using this net drop command that is like one of the surgery commands, and removing the last 3 layers that were like the final probability computation. This creates a vector of size 500, which if I take the first 50 of these 500 features, I see something like this. And you see that these are different 4s, different 6s, different 8s, and these feature vectors, they are not the same vector, but they are similar. And I like this because it means that they will they encode something about the semantic content of these images that they can use. I don't even need to use directly to compute the probabilities. I can, for example, do something like this. So what is this? You can these cells without input. You can always double click here, open. So you see, I'm using this feature space plot 3D, which is basically both doing 2 things. Is using the either an automatic extractor of the one I provide here, which is the LeNet network that we're using, to transform each image into a vector, and then it is compressing this vector from 500 dimension to 3 dimension. So basically, as you can see here, then this is some magic with image transparency, so the white of one image doesn't cover the other image. But you see, like, all the 1s are here, all the 0s are here, the 5, 3, the 7s, the 2. So this information here is all encoded in this feature vector, and just compressing this to 3D is not throwing it all away. There's still some value. I can still doing some rough classification just by looking at where these images are in the feature space. Of course, the final bit of the network, the one that I removed, is this final thing here. Sorry, scroll up here. This thing here, you see there's a 10 here and a softmax. This basically means take all this information and just put in a vector of size 10. And this is a normalization step because, probability, they must sum to 1. So I say, okay, I want to interpret, this is a common thing when you train networks. You say what you want at the end. I want to interpret this as a vector of probabilities. So the first number will tell me the probability of digit 0. The second number will tell me the probability of digit 1. Yeah, and basically setting a task and letting the network go and minimizing the error. Hopefully at the end, this model is performing the task you want. So this is how you go from an image to the numerical representation of the image, to a feature vector, to a vector of probability, to a class. Let's see how we can do this with text as well. So with text, this is slightly more complicated because for images we directly extract. We have a lot of information. One image is 1,000 words, so we have a lot of numerical values starting from the pixels. The text, we do have numerical values in a sense because the text in a computer is a bunch of bytes. Like each character it has a numerical code. So what we do in models like GPT is do something called tokenization. That we could have a session on that alone. So I'm not going too much into the details. The idea here is that there's a big string and I want to split it in like words or like pieces of words, so that I don't have like a number of words I can interpret, a number of vocabulary, like a vocabulary size which is too big, but also I don't have one that is too small. I kind of have good middle ground when I split things. And splitting into words means that each word can be connected to one integer value, which is its encoding. And if you look at the encoder of GPT-2, which is an open source network, so we can actually download it and run it, you see that this is input here. It says like a vector of n indices. This vector is my sentence, like hello, how you doing? And maybe hello is mapped to one number, let's say 2000. So I would have 2000, 1000, 3, 47. So this is how I start. But then I have to make, like, working with integers is not super nice when you want to take derivatives or things like that. So what we can do is we can try to cast those vectors, those integers into vector space, similar to the images. And we use these embedding layers to do that. So why there are two, we can actually visualize them. So what I explain it, so you can maybe a bit better understand. So the first matrix here, if you look at columns, so each column here is a vector representation of one of these. So I have like this space hello, space hello, space hello. Each one of these is a column here. And you see that they're all the same, of course, because hello, 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 this is the same word. And then I have bye, 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 and which is also the same word. So, I have half of the matrix is encoding hello, and the other half is encoding all the byes. And then I have this second bit. What is this second bit doing? Well, if I do this hello and this hello are exactly the same, yeah, in these metrics. But when I'm talking, the order of what I'm saying is important. So this second bit is generating this other branch and is what is called position embedding. So here I have one integer number for each word that gets translated into a vector. And here I have an integer number for its position, like 1, 2, 3, 4, 5, 6. And this also gets converted into a vector. And then, I do like some basic thing. I don't know what to do. So I just like sum them together. So in the end, this matrix here is equivalent to the matrix of numbers that was represented before, digits before. So it's my starting point. So for images, I start here with my 4, which you can still kind of see here. For text is a bit more complicated because I want to deal with different type of words, encoding special characters and stuff like that. And I want to know both the content and the position. But after I've taken care of this like kind of engineering details, I start with the matrix again, like this one. Okay, so we had some processing done on the image to get probabilities. So what is the main processing that happens in this in these models like GPT? So this is again from GPT-2, this open source model. This is an individual computation block, which is called decoder block. I mean, for historical reason, there's architectures where you can have both an encoding phase and a decoding phase. So this is an architecture that has only a decoding phase, but yeah, that's not really necessary to understand this. The part that is interesting here, just by looking at this sequence of operation, this is the computational graph here, is that my metrics come in here, and you can see this n times 768 means that n is the number of words, or like to be more precise, the number of tokens, because I could have like sub words. And 768 is a space where I project each integer. So for this model, it was decided to make it 768. If you want more power, you can make it a longer vector. It will take more time to train the network. It will take more time to evaluate the network. Then you see that there is this plus sign here, and there are two paths. So this is a standard trick in deep learning. Actually, when neural network became like deep learning, and you want to stack a lot of operations one after the other, there was a need to invent a lot of tricks to make it actually train correctly and reach the end and minimize this loss function. So the reason why this plus is here is because then instead of learning a function, you do an operation like this one. Your result is the identity plus a perturbation of the identity. So you will see a lot of networks like this, and the reason is because it's much easier. Like if you don't do anything, if you stay close to zero, you are just propagating the signal along. This way, there's no risk, because otherwise, if you stack a lot, you might imagine you have like thousands of operations. Each one of them, if one goes a bit awry, then nothing works anymore. Okay, so you see that there are like this thing is called like residual connection, because this is you learn what remains basically from this identity transformation. You can see here that there are like two sub blocks. This first one here is called the attention block. You might have heard this this name. We are going to go through this like in details, so I don't want to stop here too long. But you see that basically is dividing the input sequence in like in 3 bits, and then recombining them, and then adding that to the input. We have like more about this later. So after this, we have a second part, which is called the feed-forward block. And this is a lot more similar to what you have seen in my initial network. That was a very, very simple network with only linear operation. And okay, this n is normalization, just not to go too crazy with big numbers. And then you see you have a linear layer here. You have another type of nonlinearity, because there's a nonlinearity feast every few months. People like publish a new study that you can get like few percent more of accuracy, or like a few fractional percent more accuracy, changing slightly the function. So yeah, this is little. If you want to know the details, this is a little better than RAMP, because is not completely zero on the negative, so it's not killing all the information if you have a negative input. But yeah, beyond this, it's really too gory engineering details, and not really interesting. One nice thing to see here is you might have noticed that the size of a vector has changed here. It was 768, then it's bigger, and then it's smaller. This is another trick in the neural network cookbook, that you project into a bigger space. You apply the nonlinearity, which is like kind of heavily changing information there, and then you are recompressing in a lower space. So this basically gives a lot more wiggle room to the network to do mistakes, or like learn its transformation, and then kind of forces a compression. This step was was discovered to be like important. Like it forces to recompress the information to the original size, and in this forcing the compression, you kind of cut away useless information. So these are all tricks that you will then when you analyze a model in detail, you will find a lot of these things. And my feeling is that the more we work with this, the more this thing standardizes. At the beginning, there were a lot of tricks, and each group was trying their own. Now we're like solidifying on few tricks that are kind of always there. Okay, I said that I would explain what attention is a bit more in detail, because I mean this is the core concept of these transformer models. Okay, so we have this matrix, the input sequence coming in. So n again is number of words, and 768 is how I represent each and every one of them. So you see these three layers, they are matrix multiplication. So they take the sequence and they multiply this with these learnable matrices. These are learned during the training, and they are called they are the weights of the key, query, and value transformation. So this nomenclature is taken from kind of database search, and the idea here is that I have like one vector represent what I want, like my question, which is a query. I have one vector, which is a key that tells me, what is available in the database, and then I have the value, which is the actual content of the database entry. So in this specific instantiation, let's say, of the attention mechanism, is called self-attention, because all these three inputs are the same. So yeah, this is separated from the others simply because I wrote it generally to allow like something called cross attention. But this input 1, 2, and 3, they are the same. So basically, that means that I read some text, and the text is both the question and the answer, let's say. And what happens to that matrix that we saw at the beginning? It gets multiplied by these things, and it generates, like if you read here, you see that now there's n1264. So what does this mean? This 12 here is what is called multi-head attention. So this means that we have 12 heads, and conceptually, the meaning of this is that instead of processing one big vector, I have like here, I look at how this vector get processed, and you see that each key vector becomes 12 key vectors. Each query vector becomes 12 query vectors. They are a little smaller, and they are different. Why? Because what happens next? So all these vectors, they need to get combined. The query needs to ask, the key needs to provide an answer, and the value needs to be propagated. And the way this is done is by creating an outer product between the key and the query. It's actually quite simple. So I do the outer product between the key and the query, so I get a full big matrix, which basically is going to tell me how much each value is influenced by other values. So by doing this dot product between this bit matrix and the value vector, then I can recombine it with other value vectors. So the whole attention thingy basically is a weighted average. And you see this softmax here again because this is a weighting scheme. So I need to normalize these weights. Okay, so why this is important? This is important because like you can imagine that given that these values are the original words at the beginning, what I'm saying is basically how each word meaning is affected by every other word, including itself. And another interesting thing is that this is the only place in this whole architecture where I'm mixing information. I'm letting information flow between the different words. Like all the rest, all those linears layer, the non-linear layer, all the other processing is done on these column vectors individually. So this makes it very modular, and this is one of the reasons why it was so successful and scalable. And basically, this whole thing is repeated over and over, like 1 time, 2 times, 3 times, 12 times. Like some of the like GPT-4, I don't know the details of the architecture wasn't published, but it's like probably more than 12 times. It was like GPT-3 highest model. There's one little extra detail which is interesting. that when you do this multiplication, you just don't do this. You don't use this weight matrix as it comes out. You put a mask on it. So this is the actual attention matrix for a sentence here, which I have put in here. The cat is on the mat. So now each row and column is the cat is on the mat, and also here. And you see that one part of it is white. And this is because these models, they cannot see the future. So when I start reading, I read this, and that's it. What I can do with the only depends on the. But when I read on, I've already read this in the past. So while processing on, I can remix with information from the past. And Matt sees everything. So basically, this means that unless you feed back answers of something like GPT chat into itself, while it's generating text, it doesn't know what it comes next. It's not like it thinks about the whole thing and then goes back and changes that. So you can do an engineering solution that does that, but the native model doesn't do it. Like at every point in time, it reads up to that point and decides how to continue. Okay, one interesting thing about all why we spend so much time about talking about vectors and things, because these vectors have a meaning. And similarly to what we did with images, we can attempt to do we can play a bit with these vectors and try to see what we can extract in terms of meaning. So I took this is an old model called Elmo. This doesn't work with big sentences, just with words. But it allows me to show something interesting here. Look, I took a bunch of words like this: admission, recognition, filing, it, suitable, accordingly, and I'm coloring them by their part of speech. And I'm plotting them by the 2D compression of the feature vector. And you can see that even a small model like this is able to put all the names on one side, put all the adverbs, apparently it's very clear what is an adverb, on the other side. There's a bit less clarity between adjectives and verbs, but this is kind of segmenting the space of part of speech. Not super well, but still, it's adding something here. Yeah, and this is a hint about how big a model like the GPT are working. Of course, the real feature space is much bigger, and this is not working on words but sentences. But it is encoding the meaning of a conversation into this very high dimensional space. And so you could say that what is all the information of a training that this model like GPT have done? It is in its weight, and it's used to create these vectors. We can actually see a similar thing done on the full sentences. So I use GPT-3 embeddings to create this. And basically, the trick to go from a list like a matrix we've seen is always a matrix of embeddings to a single one is you just pick the last one. Given that these models, they have this causal behavior. If I look at the word that represents Matt, I can use this as a representative for the full thing because it contains its history inside. So you see here, I took I don't know, a few hundreds of Wikipedia pages with the word crane in it, and I compute the embedding for all the sentences, and then plot the 2D compression of those. And okay, this color I made, I just put a line in here, but I look at this, and basically all the dots here, they represent sentences where crane is like a machinery, while all the dots here, they belongs to sentences where crane is an animal. So this tells us that encoding the features of these sentences, there's a big part of the meaning, and I think this is very interesting. In its own, of course, if the meaning is in a high dimensional vector, of course, you can use that vector to kind of do reasoning of the sentence or like continue the sentence, because it kind of like contains the core semantical concept of the sentence. And yeah, basically this is kind of a nice visualization of the power of this. Okay, so we have a little more time. So given this is more like technical talk, I want to kind of redo this, looking at this from the code side, so we can like clarify things a bit, and I can show you like how you can play a toy game and train your own language model from scratch. Okay, so how do you need like what do you need to train the language model? Actually, surprisingly little. So there's a nice trick that you can basically train this stuff in an unsupervised way. You don't need to take input and generate yourself the desired output, because you can take like any English sentence. Like here I have like a large gray tabby cat, was lying on a rocking chair. So yeah, tabby here was split in two because it's not a very common word, so it's not in the vocabulary. And I can create a training set simply by copying the same sentence and shifting it by one. So I say, when I read A, I want to predict large. When I am A large, I want to predict gray, and so on and so forth. And the only little addition I do is I add an end here. So I say after this period, I'm done. So this is the end of my sentence. So I can create like an arbitrary big training set just by concatenating a lot of these sentences. And this is how it was done originally. Taking sentences from books, from Reddit, from Stack Exchange, Wikipedia, like stuff like Colab is trained on repository content on GitHub. So yeah, basically you have like an endless supply of training data just by grabbing meaningful sentences, hopefully meaningful. Okay, doing this will give you a model that kind of understand language, like, concepts and relationship between words, and can do like meaningful completions. But stuff like ChatGPT has another thing, which is actually turns out to be very important, which we're not going to cover today because it's kind of like very technical and long to do. So I put here, this is what you can find on the OpenAI website when I explain how they train InstructGPT. So what is InstructGPT is like some of the pilot project was done on top of GPT-3 and is a precursor of ChatGPT. And this is very interesting conceptually. And this explains what is done on these networks beside the simple continuation training. So we see that this is a 3-step procedure. So the first step is you take a prompt. Prompt is just an instruction, a piece of text, and a real person, writes what the continuation should be. So in this case, like you take something like this, and then you add some to it, and the sentence is, for example, like write me a poem, and the person writes like or selects a poem about like gray tabby cats, and then so you have like a refined training set created by human beings, and then you keep training using that. And then there's a nice trick here. So once you have this fine-tuned model, it's called fine-tune when you take the big thing and you adjust things a little. If you want to think about the arrow things, is like you block some of the arrows and you change some others. So after this initial fine-tuning, you go back to your list of prompts, and then you let the model generate a bunch of responses. And then you ask again a human being, like, what do you prefer? This is very important. You don't ask for a numerical preference. You ask for like a ranking. Like, oh, I like D more than C, more than A, same as B. This is very important because, I might say that, I like this movie a 5 and this movie a 3. But some other person might say, I like this movie a 4 and this one a 2. So the relative preference is the same. But if I have to use the absolute numbers, it's a mess to learn because they're all different. So they ask people to rank these continuations, and then they train a separate neural network to go from these preferences to actually numerical score. And then this is the final trick. you take this ranking, this reward model that tells which one is the best, actually the score of each one of them, and then you put them in a loop. So the original model writes takes a prompt, writes a continuation, and then this reward models gives a score, and then you feed the score, and now you're not really minimizing a loss which is word by word, but you let it generate the full thing, and then you score it, and this helps immensely with coherence. You don't want this to start generating random things to lose track of what was asked to. So this apparently is a very, very important step that distinguishes stuff like GPT-3 from ChatGPT and what Bing is using. So a very, very important engineering step. Yeah, we're not going to go through this right now, but I want to spend a little time detailing a bit more how you can play with this. And this is something that I wrote with my colleague, Joffre, that is going to speak in the next session, and is a GPT style network train on text display. So this you can try. It's nice because you can try this on your laptop. It takes like roughly 1 hour to train this. If you have a GPU, you can do a more interesting training. So if you get the notebook, like we took all these, there were several open repositories of text display. They're all public domain. So we put them in a cloud object. So you can just evaluate this, and then you see you get a bunch of lines here. And so what we do, we select all the things that begin with this and end with this, because there's a bunch of like Act 1 or stuff that we don't care about. And then we're going to do something slightly simpler than what is done in GPT. We are using just split by word boundary. So again, I can just show what this is. Okay, so you see, Act 1, Scene 1, London, the palace, perform, like, I split this. And then at the end of each line, at the end of each one of these lists, I add this $end that, so I want the model to learn, because otherwise there's no way to learn. Yeah, there's no special thing that this is the end. I add this end thing to say this is the end of a sentence. So I have like roughly 100,000 lines of what's supposed to say of code? Sorry, of poetry. And if I take random things, sit down, talk with her, she is thine own, end. So this is my training set. Okay, what do I do with this? I want to create my vocabulary. My vocabulary is just, I flatten everything, I take the union and to remove duplicates, and that's my vocabulary. Vocabulary is roughly 30,000 words, a bit below. The standard English vocabulary here we have in the Wolfram languages is actually 40,000. So yeah, it's a very word-rich Shakespeare. The GPT-2 tokenizer has also a vocabulary inside it. It has a lot more stuff because it has subwords and stuff like special characters. But let's go around 50,000. I think GPT-4 is now around 100,000 because they added more special characters, foreign languages. But yeah, this really depends. The more characters you add, the more difficult it is to train. But you can read more stuff. So if you only care about simple sentences or like very codified language, you might get away with fewer words in your vocabulary. Okay, let's see basically what this entails. So you see if I take, like, these are random words from the vocabulary. So we have to go from this one to a number, yeah? So I'm going to use the class decoder, which is a bit simpler than doing the tokenization thing. I'm just going to plug the vocabulary in, and basically this is assigning an integer to each word in the vocabulary. So for example, let's do this, and then I want to find the token for love. My love token in this case is 40,382. Okay, so at the end of a network, I'm going to have to go from a number to a word. So let's see. To use this gets plot out in a high dimensional space. So this unit vector is performing something called one-hot encoding. And so basically, this is a vector that is 0 everywhere and is 1 on top of the position 40,382. If I generate it, and then I invert this, this net encoder class using a net decoder class with the same vocabulary, then I can use the decoder on this unit vector, and then I go back to love, which is nice. Of course, this works also when you don't have one hot encoding, and by default it picks the highest. So if you read this long vector as list of probabilities, similar to the image and the digits, it will pick the one with the highest probability. Okay, now here I put the code that you can study a bit more in detail to define all the layers. So you can change the parameters, play the width, and adapt it to your own training task if you want to change it. Okay, so this is the embedding part that you've already seen. So my function that defines the embeddings takes my vocabulary and depth. Depth is the size of the embedding space. Yep. So my input is, for example, here I'm creating one with the depth 128 for this training, because I don't want to go to like 1000. I want this to keep this well contained. So my input is encoded in a vector. My input is also encoded with the progressive integer along the sequence. The cat is on 1, 2, 3, 4. This 50 means that I'm going to loop after 50. I don't care for very big sentences. And then I'm taking this position embedding and also making it a vector of the same depth. And then I'm summing them together. So it's quite simple to define, and then this produces what you've seen already. So thanks to this, I can take something like to be or not to be, and bam, it becomes this matrix. So this is my initial matrix to process for something like to be or not to be. Okay, then I have to create a self-attention block. This is a bit longer, but not terrible. So this is what we've seen before. Linear layer is a linear multiplication. It takes a number of heads because I want to split it in different heads. And I don't remember if I said this before. The advantage of having multiple heads and multiple recombinations, basically, because every head is recombined, is a different recombination of vectors. That means that at every step, each head can learn like a different way of recombining things. So one could, for example, focus on short range connection. One could focus on long range connection. Like it's basically giving more freedom to this model. So I want to keep the total length constant. So the depth is divided by head here. So I am taking shorter vectors. I'm encoding, you see, it's the same input, and I'm using it to create keys, values, and queries. Then I'm doing some query normalization, which is, I realized we've actually added to attention layer as an option, so I could have avoid that. I use a dot product that you saw before to create the combination. Multi-head true means I want to use multiple heads. And I'm using causal masking, so there's no peeking into the future thing. So yeah, this creates a attention layer, and then this goes back from the result of the attention recombination to a single sequence. Dropout is something that is setting some of the numbers to 0 with a certain probability, and is another trick to avoid overfitting. And then this plus here is the residual connection. I'm taking the input and I'm summing the perturbation. And then I'm adding a normalization here. So yeah, this is the custom generated attention block. Okay, then we say that after the attention, we had some extra computation using a feed forward. This is a lot easier. You see, I'm mapping. All of these are mapped. Yeah, like this is what I said before. This /at is a mapping operator. You see also here, mapped. Everything which is not attention is computed separately on each input element. So really the only remixing here is in the attention. Okay, so yeah, this is my again attention block. Feed forward block is doing this linear operation, and I see this is what I was saying. The expansion is 4 times the depth. Then I apply the non-linear operation. This is element-wise, so I don't need to map it because it's applied on every single element separately. And then I'm recompressing to the original depth. And then again, I'm doing this residual connection and another final normalization. So this is my feed-forward block, quite easy. Okay, now I have all the elements. So I can basically write this and here, like I write this as a function. I define an embedding block, which is my network that performs embedding. I assign to a variable my like a chain that is self-attention and the feed forward, and then I create the network, which is the embedding, the decoder, and then like a table of decode, like applying on its output the decoder like a number of times. So this is quite general. I can put like any depth, any number of heads, any number of blocks, any vocabulary. So you can use this if you have this notebook to do your own. So in our case, I use 128 as depth. I use 4 blocks, 1, 2, 3, 4. I use 4 heads. So if you look inside, so it's 4 times 32, 4 heads. And then the vocabulary is 1 for Shakespeare. Okay, now we have a network. Can we trade this? Almost. As we said before, we need to actually let me evaluate. Sorry for scrolling. Let me evaluate those things so I can actually show that this actually trains. Oh, I need embedding. Sorry. I need this as well. Okay, now I should have everything. Let's see. This is quite a big thing to put together. Done. Okay. So what do I need? I need a loss function. So we need to do the trick that we said at the beginning. We want to take a sentence and shift it and predict every time the next word. So here I created use function layer as a nice layer that allows you to write basically code inside and converts it to a computation graph. So I say take most input, which is everything except the last element, and rest input, which is everything except for the first element. And I say that I want to apply my decoder transformer to most, and I want cross entropy loss between the decoded most and rest. So it's much easier if I look at this. My input sequence is sent here, so it strips the last element. It runs my transformer, and then it compares with this, which is my sequence, except the first element. So because this is my target, and these two should actually be the same, and same in a probabilistic sense. So cross entropy layer is a probabilistic, like kind of probabilistic distance or error between probability distributions. You see the output here is a real number. So this is a thing that I can take the derivative and I can minimize. So conceptually exactly the same as what we saw at the beginning, just immense, like lot more parameters. Like I don't remember how many parameters has this. We can actually check if I do information of this. We had like a rough 20 parameter around the initial network. This has like 8 million parameters. So yeah, like completely different scale. Okay, so if I define this, now this network is ready for train, and I can use my lines. I put this in a net train command. So my network with the loss attached in this case. So I don't need to specify any loss function. The lines, this all means return me an object, so I can kind of look at stuff at the end. I don't have just a network, the naked network. I have like a lot of stuff. So I want to train like 3 times, basically see all the lines 3 times. This option here is nice. It's basically save 1% of what I give you here and never show it during training. Only at the end of each round, use it to measure the performance. And this batch size you can control, because the bigger the batch size, the more memory you need. So see, this was trained on like in 1 hour. It was not seeing many examples per second, around like 70, and this was done on laptop. So if I run it, okay, I'm also sharing on. So it's probably going to be very slow. Yeah. Okay, so this is much slower. You see, like around 6, 7. This is picking up speed a bit, but yeah, it can go higher if I'm not using my my computer for like doing other things like live presentation. But yeah, you can do this. You have like an error rate because it's cross entropy. This is using class, so I can estimate how good or bad it is. Let me stop this now. So of course I did this before, and I save it. You can save this in different ways. You can use stuff like cloud put it in the cloud, and cloud get. So you can do this stuff if you have this notebook, this is a public object, sorry, so you can get it. I also export it locally, so I can just do something like this. TrainNet is this. So, bam, this is at the end of the training. And so if you look closely at what we're doing here, like we are taking a sequence and we are predicting, the shifted sequence. Yeah. So the output of this is a list of vectors. If I want to generate text with this, I need to use a trick I mentioned before. I need to take the last one and then use it to generate probabilities, similarly to what I was doing with the 500-dimensional vector for the image and creating probabilities for the digits between 0 and 9. So there's one last trick here, that I use this net replace part function on the train net, and I change stuff inside the output here. So instead of mapping this linear operator and mapping the softmax to predict at each position, I replace it with this sequence last. So only take the last one of the sequence, and then I extract. The bit of surgery. I extract the linear layer from this mapping and the softmax layer from this mapping, and I put them here. So now you see, if I look at this output, there's here sequence last, linear layer, and softmax. So I'm not flattening this because otherwise I see all the stuff in here. But yeah, it's a bit cumbersome to read, but it's doing sequence last, linear, softmax. And then I'm attaching this class decoder. Class decoder is nice because, as we saw before, it's taking a vector of probabilities and giving me the class. So now with this thing, I have a model that takes a list of like a vector of strings and gives me a new string. Now I can just use it. Yeah. So if I use this nest while list, basically, because I want to use two conditions, two halting conditions. The last token has to be not, is not $end, and this is why you want to add this end thing, yeah, because you want to be able to, you want the model to be able to understand when to stop. And I'm also using maximum of 20 steps, so the first one of the two. And what I'm doing is the function I'm nesting is my neural network that you can use it as any other function. Is taking the input, and then when it's done, is attaching the result, which is the next token, to the input itself. So let's look at the result, which is a bit clearer. If I start from O, this is the unmodified O, space, my, Lord, space, I, am, N, and then it's, this is one of these small trainings, they tend to be repetitive, they're not that powerful, so it got stuck a bit. One reason why it got stuck a bit is that I'm working on what is called zero temperature. This comes from physics, and it's basically, it says always take the word with the highest probability. This is not always a great choice. It's always better to shake up things a bit. So one nice thing about networks with the class encoder is that here I'm just putting the input in, but you can put other things in. So for example, I can put an option here, which is a random sample with a probability. Sorry, with the temperature, in this case 0.7. So if I put 0, this is also starting with O. So if I put 0, I get this, and I'm gonna get this every time. If I put something higher than 0, say 0.5, then you see every time it's changing. Oops, sorry. And if the probability is super high, the distribution is going to be quite flat. So basically, there's no connection between words at this point. It's basically random sampling. O refrain, close bracket, illustrated, this is completely random. So you don't want to go too high with the temperature. But yeah, this is kind of this is trained. And a few things you can do is you can set all these sub-options at the same time, but it's not recommended. You can limit, instead of picking the best, you can sample randomly among the top 3 probabilities, for example. So this is called top K sampling. So you can put K is the top scoring words that are predicted by the network. Or you can use something a little more sophisticated, which is called nucleus sampling or top P sampling. And this basically, instead of saying, you take the first 3 words by probability or first n words by probability, is that you sort them by probability, and then you sum all the probability until you reach, in this case, 0.25. So basically, if I do this is the same as not cutting anything. But if I do this, I'm kind of limiting I'm kind of cutting the tail of a distribution. So, and as the final thing, because we're at the end, let's try to generate a bunch of sentences. So I'm going to take all words starting with uppercase, so a kind of initial bit of a sentence, and then I'm sampling like 10 of them, and let's generate this live. So this is what I had before. So yeah, here it is. So I mean, with a small train like this, it should kind of sound like Shakespeare, but not be terribly coherent. But I think it's nice that you can, this is something you can play with. This is something you can train on your own. You can let it go for 1-2 hours. If you have a GPU, it's going to be faster. But even with the CPU, you can get something done. And you can change author. You can put your own sentences or like things like that. I hope you can have a little bit of fun with this. I added a bunch of links at the end. If you wanted to read like more blog posts, there's some very good takes on transformer, on attention. Our previous lead developer, Etienne Bernard, wrote this nice book, Introduction to Machine Learning, which has a lot of downloadable notebooks and code. And yeah, feel free to click on these links and explore. Okay, we are at the end of the talk. So, Abrita, what should we do now?
Thank you so much, Giulio. We do have a few questions we've saved for you. Thanks to Mike and Juan for answering the rest. So if you don't mind, I'll go ahead and mention some of these questions.
Sure.
There's an interesting one from Mark, who is asking if we have examples of recreating the functions that the neural network is representing using basic Wolfram language functions, not the net functions. I believe we have a very simple example for the Linnet, the first layer in our tutorial. Are there any other examples?
Well, I mean, the linear layer is that we use a lot here is just a simple matrix multiplication. Yeah. So if I do linear, let me try to type this my own. So weights, and I put a matrix here, for example. So let's say 1 channel, 1, 2, 3, 4, and 1. So this should have 2 biases. I think I could have say none, so it doesn't sum anything. Oh, let's put biases. I don't know, like -1, -2. Yeah. Oh yeah. Okay. Because I want the scalar in output. This has dimensionality. What did I do here? Oh gosh. Yeah, this is why I shouldn't do this manually. You never input weights manually. Let me use our documentation.
And could you just increase magnification a little bit, Giulio?
Yes, I will. So I think we put this somewhere here. Here it is. Okay. Let's increase the magnification. So this function here, you see data weight bias dot product between weight data plus bias. So if you define this as a function, we do this. So I create this is data. I create a random linear layer, and then if I extract the weight, so I do this opposite way here. If I extract the weight layer, and you can see it here. So this is the weight layer, and this is the biases layer. In this case, it's 0, 0 because we typically initialize with 0. So if I take these two and I put it in my linear function, that was taking data, weight, and bias, and you see that the result is actually the same. Yeah, I haven't reevaluated, so this is exactly the same thing. So this thing here is basically generating this function with this array and this array as a learnable arrays. So they have numeric values that can change. And some arrays, they don't have weights, like the element-wise array. The element-wise layer which is applying ramp or these like non-linearities. They're just a function. So element-wise layer ramp. Let's go big again. Element-wise layer of ramp of I don't know, -1, 0, and 1 is exactly the same as just ramp. So in this case, the framework by default goes always floating point. So if you want really equivalent thing, this is equivalent to this.
All right. Thanks, Giulio.
Okay.
There was a question towards the beginning about the net graph plot function you were using. Is that in the function repository?
No, I should have submitted it to the function repository, but that is in the cloud. So if you take this notebook and you run this code is working everywhere, not just on my computer. So this is a kind of an internal submission to the repository that I used to I did this for Stephen Wolfram's blog, so it was quickly submitted, and I simply forgot to make it public. I will make it public at some point. I need to do some sanitization on the input. It's not very solid, but it works on simple networks. So yeah, the syntax is that you can put your network here. You can add these input arrows if you want for the explanation of what input and output is, and then you can put an input. So in this case, it has to match. So one input here, one input here, and will do its thing.
Great.
And now there was a question about punctuation that was interesting.
Yes.
So the proper way of doing this is a bit more difficult and is using a tokenizer. So we actually put this on the function repository. How it's called? Resource function GPT tokenizer. Okay. So this thing here, if you want to look at this is a subword token net encoder. So it's not a class encoder, but it works the same. It's now this can take directly a string. So hi there, how are you? And you see each one of these goes to an integer. We also want to add the tokenizer for like GPT 3.5 and 4, which is a bit bigger. Why I haven't used this in this training? Simply because you see, if you look at the vocabulary here, actually no, you don't see it here. Let me take it out. So net extract this is called vocabulary. It's called tokens. There's like all you see that there's this G strange thingy. Because like all spaces are like the BPE tokenizer. This is like very technical, but it treats space in a special way. So there's a conversion from space to other characters, and I didn't want to go into details about this stuff. But yeah, I mean, the advantage of this is that this can tokenize basically everything. It doesn't have a vocabulary because it was a thing about the tabby cat. Yeah. So if I say space cat, this is here. Big is here, but tabby, if I don't type extra things, is 2 tokens. Yeah, so this was split in 2, and this is the advantage of using a system like this. It can basically encode every crap you put in. It becomes a number. Of course, this is a thing that has to be trained if you want. But yeah, you can also use this thing directly. The rest stays the same.
The last question I had for Giulio is that we've had lots of questions about training the nets, whether on CPU or GPU. And I know in our last session, we had a question about submitting a model for training on something on the cloud.
You told me, I forgot what is the presentation. Okay, so the easiest way to do it. Okay, the super easy way to do it is if you have a GPU. So if you're on a machine with an NVIDIA GPU, you can say net train. There's actually some hidden syntax here, so let's do something quick. Net on MNIST. Yeah, so I can train this, and this goes on CPU. Sorry, I'm on a Mac M1. So given that Apple hates NVIDIA, we don't have the NVIDIA GPUs here. But if you are on NVIDIA GPUs, you can do target device goes to GPU. So we are looking into supporting right now. I mean, our backend is MXNet. We are looking to supporting more backends like TensorFlow and PyTorch that they have support for, like stuff like M1 Tensor, like neural cores. I don't remember how neural engine, how Apple is branding those, but so we hope to extend this kind of super easiness of use to like kind of other platforms. But yeah, right now it's limited to machines with NVIDIA GPUs. If you don't have it, you can use stuff like remote batch submit. This is a very nice function that I'm going to go into the documentation here and make it a bit bigger. So basically, you have an Amazon account. I think we suppose AWS or also Azure. Okay, so you can use Microsoft or Amazon accounts. And the nice thing, you can, here I send you like 2 + 2. But you can send whatever you want. You can send a net train command, and you can specify inputs files, and you can use the external storage package to specify input files that are directly on S3, for example, so you don't have to send files back and forth. So this one here is explaining how to do a color negation on a file, and you send the file here. I haven't this set up with my account, but I tried this. This was nicely. You can do like a net train command all in Azure or AWS and get back a result. So if you create an instance with a GPU or with 10 GPUs, like this, there's a syntax here, which is, where is this? Yeah, here. You can say GPU, comma all, and this will go multi-GPU, or like GPU, comma like 5, just 5, or like the GPU number 1 and number 3. It's quite flexible. It will use the GPUs that you want. Okay.